a way to bridge the gap between the tier 2 CPU work and the NVIDIA GPU nodes. Because we know that AMD GPU nodes are hard to test on, we are bridging the gap. At Antwerp, we have one partition, Arctus GPU, which contains 2 nodes, and each of those nodes has 2 AMD Instinct MI100 GPUs. Just for a quick comparison with 2 types of NVIDIA nodes, or GPUs, I would say. Keep in mind the release dates, so it's not a clear comparison. The Volta GPUs were released in 2017. The Ampere GPUs were released in 2020. And you see the MI100, which is a mid-range card, kind of hovers in between those. So how do you get started with the AMD GPUs at our site? Just as a quick example, for PyTorch, AMD has a guide on how to run PyTorch. And although we have several versions of the ROCm stack installed on our GPU nodes, AMD seems to recommend and heavily push towards a container-based approach. Those are the 4 options they give. So the first one is a Docker image with PyTorch pre-installed, one of their Docker images, a Wheels pre-compiled package, again a PyTorch Docker image, and again an upstream Docker file to build from. Useful to know, AMD already provides some of those container images through their Infinity Hub, so that is the link. Few examples: CP2K, GrowMax, PyTorch, TensorFlow. If you use one of those, you can get started right away. How you can get started is this way. So containers on the clusters, we can't use Docker because that would need root access, which we will not give. We use Aptainer. That is a way to set up Aptainer. The third line here just explains Aptainer, the command itself, build a specific container named pytorch.sif, and we pull directly from the Docker Hub to convert that container towards an Aptainer format. And then in a job script, you can put this line to run Aptainer through srun if you use Slurm, and execute a specific Python script calling the PyTorch library through Python 3 within the container. Just as a quick note, if you're planning to use it on our site, container images must be run from scratch because that is the most performing or the fastest file system we have. And then I'll hand it off to Maxime for the Lumi part.
After the MI100 series, it's the MI200 series, of course, and then especially the MI250X is what allowed AMD to nibble a little bit at the market share of NVIDIA. The closest system, geographically speaking, is Lumi, of course, the Tier 0 system at Finland, where you can get access to these devices. And as you probably know, for NVIDIA GPUs of roughly the same generation, 800 GPUs, you can get closer to home and just various Tier 1 and Tier 2 clusters at VSC have them. So if you look at the specs, I would say very, very roughly, you could say the MI250X sits in between the 800 and 800, but it kind of depends on what you're looking at. You can get a bit more GPU memory per device in the AMD case, which is nice. You also have a pretty good GPU memory bandwidth and single and double precision peak performance. When you go to half precision, you do see that NVIDIA still has an advantage there, and also the GPU communication bandwidth tends to be still bit better, significantly better with NVLink compared to Infinity Fabric used for AMD GPUs. And then the power is kind of in between there. Another thing to definitely keep in mind is that the MI250X GPU consists of 2 dies on one package, which are actually, from a software and a scheduler perspective, are actually two different, exposed as separate devices. So, but you should consider this as one GPU or 2 GPUs and one GPU. Yeah, you can kind of debate that, but in practice, this is actually 2 GPU on one package with a high bandwidth between them. And one more idiosyncrasy of this platform is that, or at least that's the case on Lumi, is that if you think, for example, okay, I have a process running on CPU core number 0 or 1 or something, which is associated with a certain NUMA domain, for example, NUMA domain number 0, you would think, maybe naively, that okay, that would then have a very high bandwidth connection to the GPU memory of the first GCD or the first GPU with index 0, but it's actually not the case. And the indices are a bit scrambled, and if you are on one of the first 8 cores, it's actually the GPU with index 2 to which you have the highest affinity. So don't worry, there's pretty good documentation on the Lumi website on how to do the proper binding in these kind of scenarios. And for getting really optimal performance, depending on the application, this might be important. Some few more examples. So Robin already mentioned the Infinity Hub containers, which in the case of Gromex is for specific versions up to 2022, and is basically AMD's port of Gromex, ported to HIP code. If you want to use mainline releases, you can sure do that, but that will then depend or rely on SYCL for acceleration via AMD GPUs. So it's a bit of a difference there. PyTorch, also there, of course, the official releases have ROCm support from a certain version onwards, but definitely, don't use PyTorch 1.8. Definitely use like 2.0 at least. 2.1, 2.2 is even better. And then on Lumi, there is actually specific containers developed by AMD for use on Lumi, which for a specific PyTorch version contains the, a suitable ROCm, RICL, Apex, all the kind of packages that you need in a typical PyTorch application. So AMD has these nice containers that you can get and use on Lumi very efficiently. TensorFlow is actually a very similar story, so I will just move on. So if you want to get your hands off any of these devices, again, for NVIDIA, you probably already know the story, Tier 1 and Tier 2 at the VSC. There's also NVIDIA GPU clouds, which might, for example, be used if you subscribe to trainings from NVIDIA, but it could be that you could also get access to GPU devices there. For AMD, Robin already mentioned Vaughan. One more thing to keep in mind is that, you also need compute credits to compute on those GPUs, but that's also a simple email to the support should suffice.
There's a project account.
Yep. For Lumi, there's something called a preparatory grant, so that you can get a small but still considerable amount of GPU resources. So you get access to Lumi, and you can compute on some partitions with MI250X GPUs there. One thing to keep in mind, though, is that it's a preparatory grant, and so it assumes that you are preparing for a regular grant, for example, and so it's you should have the long-term plan to be using Lumi in order to apply for this. And then there's also the AMD Accelerator Cloud. Also haven't tried it myself, but it looks like it should at least allow GPU developers access to AMD hardware. Just one quick slide on the underlying software stack. So you probably heard of CUDA before. Well, okay, ROCm is the AMD equivalent. HIP code is basically like CUDA code, but can be compiled for both NVIDIA and AMD GPUs. So it's slightly more portable in that respect. And just like you have the various CUDA and ROCm libraries, you also have HIP libraries, which basically wrap around both of them. So you can have one code which makes use of these vendor-optimized libraries, and the same code can, call either type of library depending on the platform that you're compiling it for. So if you have things like QBLAS, QFFT, Courant, there is the ROCm equivalent. There is also the corresponding HIP wrapper. Don't look for ROC-DNN. CUDNN is somehow called MI-open for the AMD case. Nickel becomes RICL, NVIDIA SMI, ROCm SMI. So there are a fair number of similarities there. And if you're a developer, there's even more things to take into account. As so Robin already mentioned, other programming models to consider, like SYCL, OpenCL, OpenACC, OpenMP. All of those can be used to offload to AMD GPUs as well as NVIDIA GPUs.
So now a bit about the practical aspect, let's say. We did some benchmarks in the last couple of months. Of course, both on NVIDIA and AMD. The NVIDIA GPUs were all on the tier 2 clusters in Leuven, so the Genius and Wise. And the MI100, of course, on Vaughan, as already mentioned, and the MI250X on Lumi. So I have to say, all the benchmarks we did without any specific fine-tuning for the GPU type, meaning that we, of course, if we started from NVIDIA runs, that we switched to ROCm, of course, but no other changes to the algorithm itself or any top layer or even lower layer changes to increase the performance on, in this case, AMD GPUs. I also have to say that we did runs both in containers and with system installed software. Sometimes we had to compare the both, so especially on AMD. We sometimes had to run in a container while we did runs directly on the cluster for NVIDIA. So the results, first of all, we did a test with GROMACS. This is the GROMACS STMV benchmark. It's a standard benchmark that comes with the GROMACS software. We tested on single GPUs, so not a full node, but just a single GPU. And these are the results. So higher is better performance. In this case, we can see that it actually kind of follows the generations as. And what I mean with that is that from left to right, you go from the oldest to the newest GPU. So there does not really seem to be a difference between AMD and NVIDIA. You had a question, yes?
Yeah, the AMD MI250. Are you running on one die or the two dies of the?
That's the two dies, yeah, the full GPU, yeah. That's indeed an important difference there. Then we did some machine learning benchmarks, of course. The first one we did is TensorFlow. It's a convolutional neural network for biomedical applications. Both of them were run in a container this time, and we compared runs on a single graphical processor and on two graphical processors. I use the term graphical processor here because with the AMD nodes we're talking about GCDs, and with the NVIDIA is of course the full GPU. So here it's the other way around. The lower the value, the better the performance, because we measure time per step. And you could conclude here that the A100 GPUs are performing better, but then again, we are using a single GCD in the first case. So you could also argue that it makes sense to compare this result from AMD with the first one, depending how you look at what is a GPU exactly. Then we did a test with UNet 3D, which is used for medical image segmentation, again a CNN. And here we ran on a full node, so that's 4 GPUs per node or 8 GCDs for the AMD nodes. And here we saw a big difference in performance. You see here it's the same as the previous one, it's the time per epoch. So the higher, the worse your results is. And here we see that the MI250X has a really bad performance, about 46 times slower than compared to the A100s. We had a bit of a look inside the code, what the problem was, and we see that the issue happens somewhere in the backpropagation. What exactly we did not find, and we also did not do any fine-tuning to the model to increase the performance, of course. One difference that also happens is that the AMD was run in a container in this case, while the NVIDIA runs were just with system installed software. We expect a small difference there, but it for sure does not explain the large difference we see here. Then we also ran a large language model, the Megatron large language model to be more precise. We tuned it a little bit to be able to fit it in a single A100 GPU node, and we did all our tests on a full GPU node as well. Here we see that the MI250X performs, again, before I explain something, it's teraflops per second, so in this case, the higher the value, the better your performance is. So the MI250X performs the worst, better than, compared to the NVIDIA nodes with the previous model. It's about 70% of the performance on the A100 nodes. Again, AMD was run on a container, NVIDIA was not run in a container. That might have a minimal difference. But it could be because of other reasons as well, probably because of the better half precision calculations on NVIDIA compared to AMD as well. Then, shall I skip this one? Yeah, okay. That's maybe very short. It's inference results from official benchmarks, and we see about the same between the MI300X for AMD and the NVIDIA H100. So yeah, that were our benchmark results. So what's next then indeed? So we had in the last year a lot of GPUs were launched, both for AMD and NVIDIA. I will not go over all the models, but there's a list there. So yeah, we can hopefully expect them in some of our clusters in the future. Also very interesting would be the AMD results for the ML Commons training benchmarks. I skipped a bit over that part, but it's an official, well, try to get standard machine learning benchmarks, and they have a competition that does training benchmarks. AMD will submit the results this year, but they're not there yet. We expect them in the I think it's the mid of November this year on the Supercomputing conference in the States. And then if you want to follow some GPU trainings, the VSC offers some, of course, like the Python on GPUs or the OpenMP offloading. And then there's also the GPU programming of ENCCS. Oh, that's the one too quick. And just to wrap up, what we see is that AMD GPUs are catching up with NVIDIA GPUs, especially if you look at hardware. You see that's a bit more complicated when we look at benchmarking results, especially in machine learning. That could also partly be because of the software stack that's behind it. Of course, CUDA is very mature. It has existed for a very long time. And ROCm is much more younger, so they might need some more development. A good tip is then to use the most recent versions, especially from ROCm, to avoid having issues with some of those issues. Also, expect to use more containers, especially for AMD. There is some performance issues sometimes, but installation becomes a lot more easy. It becomes a lot easier, and it might even be that for NVIDIA, the same might happen, especially because software installations for machine learning frameworks it's getting more and more complex. So containers might be a viable solution there as well. And if you want to use portable code, you want to create portable code so that you can run on different types of GPU, especially AMD and NVIDIA. Consider also the HIP and SYCL alternatives next to CUDA. And that's